T2. That's right. That's right. Okay, for T2, we can spin. I mean, T2 is T2, so we can sort of spin that way or that way. It turns out these both preserve the symplectic form, but they don't satisfy this differential equation. Let's just take the signed area off, just the flat, yeah. And of course, this doesn't have a circle action because we have sort of, if you have at least two holes, there's no way to have a rotation. Now, of course, this wasn't symplectic, but we do have a circle symmetry going around, and that will come up later. Here we have plenty of symmetries. I mean, if we think of S4 sitting in, let's see, normally we think of it as sitting in R5. If we add one more dimension and think of it as sort of sitting in the plane in R6, am I getting this right? Oh, ignore the height, yeah. Okay, so I'm going to think of this as C. So this we're going to think of as a Z1, a Z2, and a T. And I still have norm Z1 squared plus norm Z2 squared plus T squared plus 1. And we can ignore the fact for a moment that it's not symplectic. So now I should make these bigger. And then we can just act on this by, let's see, T1, T2. We'll just rotate the two complex coordinates, and that defines a two-choice action. It's perfectly nice, but we weren't in the framework already of symplectic, so we don't have this now. On here, we can act by a circle and a circle independently. Yeah, it's just a product action, and so so here we can. So it seems like a silly thing to do, but we can actually scale the symplectic form. So remember, symplectic form is just telling you area, and so it's sort of telling you how big your sphere is. So I can think of this as a little tiny sphere, product a really big sphere, and then my momentum map lands in R2. And this will go to sort of a rectangle rather than a square. Okay, but we could scale it to whatever rectangular square that we want. CP2, let's see. Oh shoot, I got something wrong. This should have been in C3. So C3 has a T3 acting by rotations like this. And if I apply a rotation to C3, I can apply a rotation to a subspace and we get some other subspace. So T3 acts on all of this. However, the diagonal TTT is going to send every line to itself just so bigger, but it's not going to change the line. And so this has an effect of a faithful T2 action, which I can think of as T3 modulo the diagonal circle. And that has momentum image, a triangle. That's right, phi is the momentum map. And this theorem says that phi of m is always a convex polytope. More than that, it's the convex hull of the images of the fixed points. It's unique up to a constant. It's defined by a differential equation, and so you can always sort of adjust your function by adding a constant. Which one? The CP2? Yeah. So the action. Maybe it's better if I write out CP2 in coordinates. Okay. So in CP2 we can think about homogeneous coordinates. So I just think of a Z0, Z1, and Z2 defining a plane inside of C3, and lambda Z0, lambda Z1, lambda Z2, if I multiply them all by the same complex number, they define the same plane. So these are my coordinates. And then I'd like to do, so the T3 action on CP2, coming from CP3, just says that T1, T2, T3. Oops. Oh, sorry. That's awful, but that is what it is. Okay, so I just rotate each coordinate, and so then I change my plane. And in this way, so also we can see that TTT is going to fix it, because it's going to send Z1, Z0, Z1, Z2 to T1, KTTT. So it's really only a T2 action, so I can just sort of forget about this one say. And what the momentum map is, if I write it in those coordinates, it's going to send Z0, Z1, Z2, 2. And it better be a homogeneous function in order to be well defined. And what it's going to send it to is Z1 squared divided by the sum of all of them squared, Z2 squared divided by the sum of all of them squared. And the image of that is the convex hull of 0, 0, 1, 0, 1, 1. Exactly, the extreme points and the points that are fixed. If I have 1, 0, 0, that's not going to move under this action, or 0, 1, 0, that's not going to move under this action. And so those are the fixed points, and that's exactly this again. Sure. Oh, and then I would have had to, I should have written the symplectic format. Oh my goodness, okay. Okay, it's not, I can say it's a differential equation, but it's, well, actually, you prove this. The proof is by induction. The proof that I know better. So they have different. Atiyah and Gilman and Sternberg had different proofs. Atiyah's proof is by induction on the dimension of the torus, and in one dimension, you can see this fixed point business pretty easily because in one dimension. Oh, I have to write down the differential equation. Okay, but in one dimension, what you can see, you have this function, and you can see that the critical set is sort of naturally the fixed points, and well, the extremal points have to be critical. So it's not saying very much in one dimension. But then you have this bootstrapping technique where this is related to the fact that the level sets of this map are also connected. And so there's this bootstrap back and forth between the level sets being connected and then bootstrapping it up to the next dimension.
And the other show that's locally around 8 points of the whole sort of thing, and then also the whole other sort of thing. And if it's not fixed at all, then They do, and I'll talk about those in a special case. I haven't figured out how to use them in every case. But the first thing you need to think about is whether the manifold is simply connected. And in the simply connected case, you still have this very nice H vector, F vector correspondence. Okay, but the first thing you show, so we were sort of, so I proved this with Anna, but we were building on some earlier work up in Masuda and Park. So pi1 of this manifold is isomorphic to, well, first of all, we're taking the origami template off the torus module with something, and so you sort of expect any cycles in the origami template to still contribute to the fundamental group, so that's true. The fundamental group of M is isomorphic to the fundamental group of the orbit space, cross, you have to add a little finite, well, maybe not finite. What this is a lattice correction. So let me say, first of all, what each of these factors is, and then I'll give you examples for how they show up. So this, that's the fundamental group of that origami template. It turns out the origami template, everything definition retracts to the template graph. So this is really just the fundamental group of the template graph. So it's a free group. And let's say it has rank K free group. And then the correction that I added, this is just a lattice correction, and what it is you take, so N we think of as the full lattice, ZD, and N sub the orbit space is the span of these new F's, those normal vectors to the facets, for every facet that I haven't glued. Okay, so I take the Z-span of all of those things. Most of the time, that's the whole lattice. But the point is, like in these examples, if I had a fixed point, then all of the edges coming out of that fixed point Z-span, that's equivalent to saying all of the normals to the facets that meet at that vertex is Z-span. And so if there's a fixed point, that lattice correction goes away. So it's only when I sort of glued all of the fixed points that I could potentially have an extra correction. And because of this business because I always have D minus one facets still around for any edge in the origami template, this is at worst a co-rank 1. So this correction is either going to be a trivial group, a finite cyclic group, or a copy of Z. And all three of those can show up in this simple example, it turns out. Okay, so if I take template graph, that, and if my two pieces are, let's see, I can do rectangles, I can do something with slope -1, I can do something with slope -L, those are all Delton polytopes. And then if I take two copies of each of those and glue along the top facets and along the bottom facets, I can just look at the lattice correction. So here I have my normals are the same, and so they only span the Z, so my lattice correction is going to be Z. Here, let's see, I have -1, 0, and 1, 1, those Z span, so I get a trivial lattice correction. And here, I have something like that. Looks like a Z mod LZ. You can actually explicitly identify the manifolds in this case. So in each of these cases, N, let's see, so here N is going to be F3. No, sorry, F2 cross S1 cross S1. Here we're going to have S3 cross S1. And here we're going to have a lens space cross S1. So lens space is just a sphere divided out by a Z mod L action, a free Z mod L action. And so this has fundamental group, well, there's the Z mod L Z for this and the Z for this. Here we have a Z for each factor. Here we just have a Z for the S1 factor. And here we have a Z mod L Z and a Z. Okay, so all three of those can occur. Okay, this is sort of, these are sort of the exceptions, and sort of nicer things happen when you're simply connected. Okay, so well, so actually what is true is that O is simply connected if and only if M is simply connected. So you can only, so if M is simply connected, well, both of these have to go away, in particular this has to go away. But if this is simply connected, well, it turns out then you have to have a fixed point, and so you can't have this lattice correction. So this is an if and only if. And what happens in this case is that you do get, again, this F vector H vector business. Okay, so what I mean, you have to be careful how you count. We no longer count anything that's on one of the glued facets. But for example, actually I'm going to do, yeah, so what I should say is the F vector here is counting the number of K facets, K faces of O, and here you do the same translation, but what this ends up counting is the Betti numbers of M. Okay, so this fact is due to Masuda and Panoff. Yeah, Masuda and Panoff implies this. Okay, and so this business of counting carefully, I'll show you a quick example. So we can do S6 in the same way as we had S4, and I'm doing S6 just because it's a slightly bigger polytope. Okay, in both cases, what happens is that the template graph is this. Each vertex has the same polytope, a simplex, and the facets that I glue, I take two copies of that and I glue them along this. Okay, so that's my O, sort of superimposed. Okay, and then the point is, when I want to count, it's easy to count vertices. I just don't count things on the pink, so there are two vertices. There are three edges, because there are edges that, so this vertex can go up. I can go back into the board. Oh, no, I'm not supposed to use paint. I can go back into the board. Or I can go along. So there are three edges. And then there